I promise that this is the very last virtual memory lecture that we have in CS124 for the year. In fact, I should probably mention that we're getting close to the end of the lecture sequence for the year, as I'm guessing you would imagine, because we are getting into the second half of Project 4. Project 5 is the last project for CS124. And so after this lecture, we're actually going to start talking about file systems. And I don't have a great deal to say about file systems, but certainly some material that will help you in your implementations and understanding and so forth. So today we will finish the virtual memory discussion with something that actually isn't particularly pertinent to Pintos, because it has to do with another aspect of virtual memory management, which is how do we decide which processes get how many page frames? This may be a question that you hadn't considered until now. We call it the page allocation policy. Most of the time, all we're caring about is when we need a new frame for a page, we need to take that frame from somebody. And so we spend all of our time thinking about the page replacement policy. But the page allocation policy is a similar but slightly different consideration. So the OS needs some number of page frames for itself. This is what you all have encountered already quite a bit as you've been going through the Pintos implementation. We have a kernel page pool and a user page pool. And the same is true in real operating systems. You have some number of page frames that are necessary to run the kernel. I've mentioned before that some kernel implementations are intelligent and they are able to page in and out kernel data structures and kernel code. There's always some part of the kernel that must stay in memory though, and at the very minimum, it's got to be the page fault handler, because if the page fault handler is paged out, then what is going to bring the page fault handler in? And maybe you might say the double fault handler, and I would say then your OS is too complicated. Just leave the page fault handler in memory. So the OS is going to require some number of frames. And then all the remaining frames that we have in physical memory, we can devote to user processes, holding data for user processes, holding code for user processes. But we want to do this in an intelligent way. And so the OS has a few things it can control. As I say on the slide, it can control how many frames are allocated to each process. Now you might think about Pintos as you're implementing your Pintos pager, and you'll say, I don't really think about how many frames are allocated to each process. But you could, if you were so inclined to do so. You could keep account of how many frames are assigned to each process, and you could set limits on that so that when you're making eviction choices, you could decide what process should have its frame taken away. And maybe the frame that faulted should have some other page evicted so that its frame count remains constant. So you have these kinds of choices as an operating system. And then also the degree of multiprogramming, which is simply the number of processes that we're trying to run on the operating system at any given time. You may remember that this pertains to medium-term scheduling, because medium-term scheduling is about removing processes that could run from the scheduler so that we can reduce the degree of multiprogramming. We're not trying to run as many processes at the same time. We don't generally do that on our modern operating systems. Like, I've got my cell phone here. I'm talking to my Mac while I talk to all of you. And I don't have a medium-term scheduler on those things. You normally see that in a batch processing system. So degree of multiprogramming tends to be a little bit more of a batch mode type concept. So the page allocation policy is the thing that decides how many frames should be assigned to each process. And you do see this given consideration in certain kinds of operating system implementations. So the main goal is we want to make sure that every process has roughly as many as it needs. That would be the ideal goal, that every process has enough frames to perform the task that it's trying to perform. If we lived in a perfect world and we had computers with way more physical memory than anybody wanted to use, programmers were very careful with memory allocation and resource usage, and memory was very free or very cheap to get from manufacturers and so forth, then we basically would only ever have page faults when a program began accessing data that wasn't already in its virtual address space. That would be the only time we would ever see faults. And our programs would run as fast as they possibly could. In fact, we could be even more idealistic than that and say, hey, let's just always allocate frames to processes every time they say, I think I might want to use that address range. So we could do that too. So we tried it, this would be the ideal if every process had all the frames that it has, but that's not reality. Like, reality is far more limited than that. And so we'd like to do more work with less, or I should say fewer resources. And so generally what we try to do is keep the page fault rate to something that's not horrible. That's kind of the goal. Keep the page fault rate to something that's not horrible. And it turns out that there is a level at which it's horrible, and we'll talk about that pretty much right away. So given process page faults, it slows down that process because, you do the access, you get into the fault handler, that traps into the kernel. The fault handler says, I've got to perform an I.O. That I.O. takes anywhere from a few 100,000 clocks to a few tens of millions of clocks. So that process is now dead in the water for a little while. But that's okay, because that means some other process could get the CPU. And so that's why I say here on the slide that in the context of multitasking, faults aren't that bad, because it's kind of another way to kick a process off the CPU and make it go away for a little while so other processes get the CPU. So we kind of don't mind them. Like I say at the very bottom of the slide, as long as we keep the I.O. due to page faults at a reasonable level, so we want to keep that page fault related I.O. to a reasonable level, then overall the OS can continue executing user processes and everybody can make progress. We'll keep that CPU utilized at 100% utilization. Okay, so that's kind of the realistic goal. We're going to try to do as much as we can with the resources that we have on hand, and we'll try to use them as efficiently as we can. Now, it is possible for the paging I.O. to grow to the point where it starts to impede system performance. And the way to think about this is you have some number of processes running on the system, and each process has a working set. Remember, the working set is the set of pages that the process currently needs to be in frames so it can do what it's doing. And so you have a set of processes, they each have a working set, and the working sets of all the processes don't fit into physical memory. And so a process starts to run and it faults, and some other process loses a page from its working set that it needed. And so the first process is now blocked on I.O. Some other process runs. It faults. And then another process loses a page that it needed in its working set. And so you basically see that every process is A, faulting, and B, causing other processes to fault. And this basically means that the whole system grinds to, I shouldn't say it doesn't grind to a halt. It just slows to the speed of molasses on a cold winter day, because every process is now running at the speed of the disk. One of the things we like to say about hardware caches is it gives you a memory the size of DRAM, but the performance of the hardware cache, which is going to be typically an order of magnitude faster, possibly even more. The worst case is when you have a memory the size of your disk and the speed of your disk, because your disk is horribly slow. And so that's what we call thrashing. Thrashing is an exciting sounding term. And as I say on the slide, thrashing, the concept of thrashing came from when mainframes used reel-to-reel tapes to do their swap storage, to do their persistent storage. And those things started to sound appalling when the system started to have this kind of very heavy page fault rate. It's called thrashing, and so that's where the term came from. You can also have an individual process thrash. It depends on your page allocation policy. If you have one process that's gonna misbehave and it wants its working set to be as large as the address space, and your allocation policy is a process has a constant number of frames, then that process could basically only hinder itself and allow all the other processes to continue on sort of unabated and unhindered by that process's bad behavior. So you can have an individual process thrash, or you can have your entire system thrash if every process can steal frames from other processes that are running. Okay, so as I say here, thrashing occurs when the total number of frames that processes are using exceeds the number of frames available in the system. And so you get this behavior. Every memory access, or let's say you only get to go a few memory accesses before you generate another fault. And so the whole system's performance starts to be governed by the disk as opposed to by the performance of DRAM. Okay? Terrible situation to be in. I'm really curious. I'm just going to ask this. I'm going to ask this, and you don't have to respond by talking, but you can respond in chat if you want to. When I was a kid and we had Windows was sort of the first operating system that I used that had this idea of swap and page faulting, because DOS didn't run on a computer clever enough to include virtual memory. But every once in a while, we get into the situation where everything on the computer was running super slow, and the little hard disk access light on the computer was just on constantly. Or maybe if you looked really carefully at it, it would like flutter. It would just flutter a little bit. But it was basically on. That's how we knew the computer was thrashing. You could hear the disk just going a mile a minute. Nowadays, with modern computers, you don't really have that so much, especially because solid-state drives are so much more efficient. One of the big things that makes thrashing so expensive is the disk seeks, and you don't have that with solid-state drives. And, not to mention that solid-state drives tend to be 2+ orders of magnitude faster than spinning magnetic disks. So I'm curious if any of you have had experience with thrashing. And so that's, if you have had experience with thrashing, if you've seen that kind of a circumstance in any of the computer systems you've used, I'd love to see if you'd mention on chat, because this is kind of one of those things that's less and less common now. Okay, so let's say that we have a computer, and it's got 20 physical page frames that are available for applications to use. You've got 4 processes running. Each process needs 5 frames. 4 times 5 is 20. We're okay. We're pretending the OS is a massless, frictionless OS, so it doesn't need any frames itself. So if we had 2 processes suddenly change to where they needed 10 frames instead of 5 frames, now the overall system requirement is 30 frames, but we only have 20 frames of physical memory. And so you can see in this kind of a circumstance, the system would immediately start thrashing. Okay. And so if you have a global page allocation policy where any process is allowed to assume ownership of a frame from any other process, then that means all the processes start to fault. All the processes' behavior starts to be hindered. Oh, here's a comment. I got my first laptop in 2012. I had a 500 gig hard disk, 4 gigs of RAM, and it would start thrashing whenever you'd use it for more than an hour. Yes. So you definitely run into these kinds of issues. Unfortunately, with thrashing, there's only 2 real solutions. One is to increase the physical memory on the system, and the other is to just use less memory in your programs that you're running. And if you can't do either one of those, you're just sad. And so I remember that happening quite often. I found it mystifying as a computer behavior as a youth. I was interested in computers from the age of about 10, but whereas I found it slightly mystifying, my parents were just frustrated because they didn't care about how computers work. They just wanted to use them. Okay, faults and degree of multiprogramming. So yeah, I was already talking about this. Processes have a set of pages that they're working with that's called the working set of the process. And the degree of multiprogramming is just how many processes am I running? So it's not a very exciting number. It's 8. It's 41. You know, how many processes are we trying to run at a given time? And so qualitatively, you'll see the behavior that's described by this little graph in the bottom right of this slide. That as you increase the degree of multiprogramming, you start increasing the overall requirement for frames on the system. You also increase the CPU utilization because programs do need to read data. You know, these aren't compute intensive processes. You know, you're still going to have IO bursts, which will cause a process to get off the CPU and other processes can run. So you increase the degree of multiprogramming, and as the frame requirements increase to the point that they approach the total available frames, then you start to max out both the CPU and the IO system. And suddenly, once you've maxed out the IO system due to faults, that's when you see the CPU utilization drop. And so that's another characteristic of these systems that fall into thrashing, is like the disk controller is maxed. It is like, I am so busy, I can't do anything else. And the CPU is waiting around for data because the CPU can't even get instructions to run without faulting. So the CPU is basically just waiting around for IOs to complete. It's a bad situation to be in. Okay. If you can control the degree of multiprogramming because you happen to be a batch processing operating system or something like that, then your medium-term scheduler would say, all right, I'm going to reduce the degree of multiprogramming to try to get the fault rate under control. And so, yeah, the long-term scheduler is going to maybe not admit new jobs because the degree of multiprogramming is too high and the fault rate is too high. Medium-term scheduling is like, the program is, or the system is really misbehaving, so I need to pull some processes out until things get under control. Okay. And so you can definitely see these kinds of schedulers take fault rates into account when they're making their decisions. And the nice thing about it, I can't remember if, I'd have to go back and look at Pintos, but I was just looking at the code today when I was looking at some questions that students had. You can track the fault rate on a per process basis. Like your kernel can track a lot of things. And if you see that one process has a huge fault rate, in that it is generating faults, and other processes have very low fault rates, suspend the process that has the high fault rate. So you can have your medium-term scheduler be quite clever about how it makes these decisions based on the statistics of what it sees processes doing. Okay. So pretty clever kind of techniques. We'll talk about some other techniques as we get toward the end of this talk as well. Most of the time, we have systems that don't have long-term schedulers or medium-term schedulers. Or if you will, the long-term scheduler is the user, and the medium-term scheduler is the user. And if the user says, wow, I'm grumpy about how the system's performing, then the user suspends processes or kills processes or whatever. And so that tends to be the approach of general purpose operating systems. We only focus on short-term scheduling. Okay, so yeah, performance becomes unacceptable, for example, due to thrashing, then the user simply terminates some processes. Okay, so hopefully that will fully explain this notion of thrashing, which I hope you will never encounter. I'm kind of sad because it's kind of an interesting and fun problem. And I'm trying to think if this is a problem that we need to be aware of. Modern computers are getting larger and larger memories, larger and larger address spaces. And so obviously, as you have more frames, and programs don't necessarily use all of the frames. So I'm not sure how much thrashing will be an issue going on into the future. I have a feeling that, a couple of lectures ago, I talked about non-uniform memory access and symmetric multiprocessing and memory layouts. And I think that's probably a much more serious modern memory management issue than thrashing is necessarily. You will still nonetheless see swap and thrashing occur in systems, but its impact is probably going to be much better than it used to be. Let's say a decade ago, even as recently as that. Okay, let's see. So a process needs a frame. The OS has two options. It can either take a frame from any process that's running. We call that a global replacement policy. So process A faults, the OS evicts a page from process B's set of pages and assigns the frame to process A. And so with a global replacement policy or a global allocation policy, it allows you to increase and decrease the number of frames that a given process, quote unquote, owns or is using, okay? So yeah, this gives you a lot of flexibility because it's just reality. Processes don't have the same working set sizes. You can't even necessarily infer the working set size from the virtual address space size. It may simply be that one process is doing a lot of intensive memory work and another one is not. And so a global allocation policy or a global replacement policy is kind of nice. The issue with a global replacement policy is that a faulting process can affect other processes. And so this is where you get the entire system thrashing if the total working set sizes of all the processes. Basically, it's like you can have one process be the domino that causes the entire thing to collapse. And that's the part that kind of sucks. A local replacement policy or a local allocation policy basically means the OS really strictly controls how many frames are available for use for each process. So if process A faults, then the OS is going to pick a page from process A to evict to free the frame for process A to use for this new page. And so you can see here that this is going to be a lot stricter about how many frames each process really gets to own and have. Okay. So the nice thing about this is if one process is badly behaved, it doesn't affect all the other processes nearly to the same effect. It's mainly going to slow down that one process if it starts to thrash. But the issue with it is obvious from the discussion on the previous slide. This isn't very realistic. And most of the time we want to vary the number of frames allocated from process to process based on the process's working set size. I mean, you can think about two programs. You could have two instances of the exact same program running. And just based on the arguments you pass to the program, they may have very different behaviors with respect to memory usage. If they're processing input files, like say a compiler or some learning system that's doing training or something like that, based on the inputs, the memory usage behavior may vary wildly. And you'd like your OS to be able to proportionally allocate frames to processes based on the process's needs. So it tends to be that modern operating systems pick global replacement policies, not local ones. Okay. Let's see. There are some very simplistic, I know the slide says simple, but I'm going to say simplistic page allocation policies. I find these uninteresting, but you should still be exposed to the information. So you have a total of M frames, and they're able to be allocated by N processes. We need to share them across N processes. So we could just say, all right, we'll divide M by N, and then each process gets roughly that many frames. So that would be called an equal allocation policy. If you look at the virtual address space, you could say this amount of the virtual address space is allocated in the process, and you could use that to scale this allocation policy across multiple processes. And so that would be a proportional allocation policy. So this process has a huge heap. This process has a tiny heap. This process has a lot of shared libraries. This one has none. You could have situations like that. Sorry, I'm getting a phone call. You could have a situation like that where you look at the size of the allocated address range in the virtual address space, and you could use that to proportionally allocate frames to processes. Okay, so that would be a proportional allocation policy. I don't like them though. They're not very, like I said, they're not very intelligent. And a lot of times we want our systems to be a lot more intelligent than that. They would make sense with a local replacement policy because you have to somehow figure out how many frames should be given to each process. And if I were stuck in that universe, I'd probably go with the proportional allocation policy. Now, you do have this thing that with these policies, let's go back a slide. What's underneath the bottom? Well, it's either N, which is the degree of multiprogramming, or S, which is the sum of the address spaces of all running processes. So both of these things have something in the denominator that gets larger as the degree of multiprogramming goes up. And so you can see that the processes will individually end up with fewer and fewer frames, okay? So these frames have to come from somewhere, and so as you grow the degree of multiprogramming, processes that are running are losing frames because you have to. And so you have to use medium-term scheduling to make these systems behave when it comes to the specter of thrashing and the whole system basically grinding to a slow crawl. Now, another approach is to use the working sets. You remember at the very beginning of this talk, I was saying you can use the working, or you can think about the working set of processes as being the thing that limits the behavior of the virtual memory system, because processes do have a working set. And if the working sets don't fit in physical memory, you have a problem. And so what we can do is, just like we talked about with page replacement policies, we can try to estimate what the working set would be, okay? And so we have a technique that we can use that's very similar to some of the stuff we talked about. What we can do is use that window type mechanism again, where we have a periodic timer interval that goes off, and we take from that point to some point in the recent past, and we have that window, and anything that was accessed within that window we consider to be part of a process's working set. And so, of course, that means you have to choose the window size really carefully, or else you'll end up having problems. And so in this case, the window size is tau. This is basically identical to what we were talking about with the replacement policy, with one exception, because we're not doing any of this WS clock, virtual clocks, timestamp kind of stuff. Instead, we actually use a very simple approach to estimate the working sets of processes. We use aging. We use a very coarse version of aging. Maybe we have 4 bits for age, or maybe we have 1 bit for age. And what we do is we have a very long timer interval for ticks for this part of the system's behavior. And so, like I say here, the OS maintains a B-bit value for each page. And so on a periodic interval, we traverse all the pages that are in memory. We look at the access bits for the pages that are in memory, and we update the age value using the mechanism I described in the previous talk. We shift it right, and we drop the current value of the access bit into the topmost bit. So if it hasn't been accessed since the last time we checked, we put a 0 in there. If it has been accessed, we drop a 1 in, okay? And so this is a much coarser grain mechanism. I hope everybody's getting that. You're looking at this and saying, well, that sounds exactly like aging. Yeah, it's just a lot coarser grain than the aging model used for page replacement. And we just say if the processes page has a non-zero age, we consider it to be in the working set. If it has a 0 age, we consider it to not be in the working set. So whatever that B bits is, so whatever B is, times the timer interval that we use to update the age. So the product of those two things gives you the size of your window. That's your tau. And so you can use that to do a very simple working set estimation. Okay, so this is what I was describing before. The main difference between this and aging is simply the very coarse nature of this model. Okay, hopefully that makes sense to everybody. Now you're using this. One of the things that I want to mention is you're actually using this to determine the set of pages that are in the working set. Okay. And so you can use that to determine the degree of multiprogramming. So you can make decisions like, the total of, all working set sizes is the number of frames right now. We have a problem. We need to reduce the degree of multiprogramming because the total set of working sets is as large as the entire, size of physical memory. Okay. If we have a sum of the working set sizes that's smaller than the number of frames, we can inch up the degree of multiprogramming. We can start running a few more processes. Okay, so we can do something like that. And yeah, so this works well. I'm going to hide that for a second. Linux does something kind of like this. And I want to mention that this is not really used for doing things like page eviction, because page eviction policies tend to be much finer grained than what we're talking about with page allocation. Page allocation tends to use these very coarse grain things because you're talking about general trends in the system behavior and nudging the general system behavior in certain directions in a hope that you're going to have it run efficiently and effectively for everyone. Now, the other part of this that's really kind of neat is maybe you have a process and you're estimating its working set, which means you're trying to figure out which pages is it actually using right now. And then it becomes blocked on I/O. Now it becomes blocked on I/O, and so you can start paging out its pages because you want to use those frames for something else. Then you have something happen that unblocks the process. And your OS can be clever and say, well, I know that process is working set, so what I'm going to do is start paging in all of the pages that are in the working set now that I know this process is ready to run again. And ideally, this will minimize the number of page faults because you're guessing that's still the working set, so you're guessing that all those pages are actually going to be accessed again in short order. So that's why I'm saying that using a working set model can be used to drive these pre-paging type decisions. Because if you have a good guess of what pages a process is using, you just load them, get them into memory, and let the process carry on once it's unblocked. So this is a pretty neat technique that can be used. I don't know if there's any questions about that. If anybody's got any questions, feel free to ask. Page fault frequency is a super helpful statistic that an operating system implementation can track to figure out if it's made bad choices or it needs to tweak any choices that it's made. So as I say here, the page allocation policies I've described make sense in the context of medium-term scheduling, okay, where you actually can control the process scheduling mix. And so since we don't have a long-term or medium-term scheduler, we can use the measure of page fault frequency to guide decisions about where more frames are needed, okay? So you can, like I said, you can track the page fault frequency on a per process basis because, I mean, you all have seen this by now, I expect. You end up in the page fault handler, you know what process got you there. And so you can have a page fault count per process. And if you see one process that's got a crazy high number of faults, you can say, well, maybe I should assign it more frames. And so you can do those kinds of things as well using the page fault frequency inside of an operating system implementation. Okay. Yeah, and if you have a process with low page fault frequency, then you can say, I can afford to take away some frames from this process to assign to a process that has a high page fault frequency to try to balance this out a little bit better. Okay, so yeah, this is used in some operating system implementations. I think Windows is probably the most notable example, because in Windows, you can actually say, these are my virtual memory requirements. This is how many pages I want to have. So Windows actually has the ability to say that kind of thing. You've probably never written a program that says those kinds of things to the operating system, but some OSs provide that kind of an API for the specific problem. So as I say on the slide, Pager can aim to keep process page fault frequency within a specific desirable range. So you have sort of a lower and upper bound that you try to get within that seems to yield good program performance. The CPU stays fully utilized. The IO system is reasonably well utilized without being overwhelmed. And so if a process has a page fault rate that exceeds that upper bound, then you start taking steps to give it more frames from processes maybe that are on the lower end of that range. Okay, so you're probably bringing up those processes lower bound on their page fault frequency. If the process is below the lower bound, the OS considers it a candidate for giving up frames. So you can start, remember we talked about page buffering a couple of lectures ago. You could start just taking away frames based on usage, of course, but you can start taking away frames from that process because you say, you know, your page fault rate is really low. I think you'll be fine if I take away some frames. And of course, if it's in that sweet spot, it's between the lower and upper bound, then the OS can do other things. It can basically leave the frame allocation alone and do other things like use LRU, use the eviction mechanism to identify possible candidates for eviction. Like, this page hasn't been accessed at all for a long time. Let's make it a candidate for eviction. Okay. Let's see. Yeah. So this won't necessarily prevent thrashing, but you know, this is one of those things. It's hard to solve this problem in a nice general way. And if the user is intent on running too many things, you're getting thrashing. You're going to see thrashing regardless. If every program that's running is using a huge amount of memory and it's got a really bad locality of access, then you're going to see thrashing because it's just not possible for the OS to keep the working set of every process in memory at the same time. So, you know, you could still use medium-term scheduling in that kind of a situation. Okay, last few things to talk about, actually. We may wrap a little early today, which would be a nice change. I'm sure you all agree. Most operating systems keep things pretty simple when it comes to page allocation. They focus most of their effort on the page eviction policy, and they use this beautiful thing of the page buffer. Remember, the page buffer can have clean pages and dirty pages, but these are pages that are candidates for eviction, not actually evicted. And when a new page needs to be, let me see if I can say this correctly, because I need to use my terminology correctly. If a process requires a new frame to satisfy a page in need, then it can take from the clean page pool and satisfy that request immediately. So that tends to be the approach of modern operating systems. Let me spell this out here. So we rely on a sophisticated page replacement policy or eviction policy. Those mean the same thing. And we use global replacement so that as a process's frame requirements change, we can adjust to those very easily. We let users make the choices about what they want to do, and we hope they will be savvy enough to not do too much and to stop programs if the system starts to become overburdened on performance. And if you have a process that is blocked for a really long time, then what happens is the pager starts getting rid of the pages that that process is using in physical memory, because it'll say those pages haven't been used for a super long time. So we might as well start evicting those pages and using the frames for some process that is running. Okay, so that just kind of happens naturally. And I've mentioned before, like if you ever have had the experience of working on a term paper or some other delightfully pleasant writing experience where you're using Microsoft Word or you're using some other tool like that, and you just walk away from doing it for a few days, and then you come back and you click on it, and it takes a few seconds to actually come back and start being responsive, it's because that program's pages were virtually all moved to swap, and the frames that the program were using were being used by other programs because the program just wasn't doing anything. It was blocked, waiting for you to get back to it. And then once you click on it and start interacting with it again, all those pages have to be brought in from swap, and they have to be moved into frames again. So you have eviction going on, you've got swapping in going on, and so that makes the program take a long time to resume. You know, a long time typically being half a second or a second, but it's noticeable because we get pretty used to computers being instantly responsive these days. Okay, let's see. Final few things to talk about. Linux has a very simple, I shouldn't say simple, but it's intuitive based on everything we've talked about over the last 5 or 6 lectures. Pages are never allocated to a process until they're actually used. So this is a pretty much a pure demand paging approach. The program may have virtual memory references set up in the address mapping, but then page faults are what actually move information into the process's pages. So, so it's a pure demand paging type approach. Another example, heap and stack aren't allocated to a process until it actually references pages. So you do that malloc 30 gigs. I would love a piece of memory that's 30 gigabytes in size. Malloc turns around and says to the kernel, man, this process wants 30 gigs of memory. Can you believe it? And so the kernel adjusts the heap size. It moves the end of BSS to wherever it needs to be, and then returns. And malloc says, okay, here's your 30 gigs of RAM. And you don't have any frames for, you don't have 30 gigs of frames because that would be scary anyway. But once you start touching the memory and faulting, that's when the kernel says, okay, I'll start giving you frames because you're actually using what you asked for. So it's kind of an interesting model. Like if you go to the bank and say, I want a $10,000 loan, they give you $10,000. But imagine instead that you had a magic wallet and you went to the bank and they said, you said, I need $10,000. And the bank says, okay, you can have $10,000. And you open your wallet and there's no money in there. But every time you're like, oh, I need $30, you pull out $30, it magically appears. And that keeps happening until you pull $10,000 out, and then it just stops. So that's much more like what operating systems do with virtual memory. Okay, yeah, Linux uses something like clock. Now, it's interesting because Linux has page eviction. It's pretty sophisticated about page eviction, but it uses a modified form of clock to keep track of page ages. And it will periodically traverse these ages, and it will, how shall I say, decrease them. It will degrade them in some way so that ages sort of start out and then they drop off relatively quickly. So they drop off precipitously initially. And part of the reason why is because you can have the same issue of scans in DRAM, just like you can have it when you're scanning a file and bringing data into memory. And so Linux is tuned, its page usage policy is tuned to be scan resistant, so that if you're doing an operation where you scan a bunch of data and you access each page once and then you don't access it again, the pager will say, oh, okay, well, I can reclaim this frame pretty quickly. Okay. And so that's why I mentioned this here. Really good policies when it comes to caches and so caches, I'm using a general term here. So that includes both the DRAM cache of disk, the file system cache, those kinds of things. So you'll see it in virtual memory. You also see it in the file system cache. We want to examine recency and frequency. We really need to do both so that we can be scan resistant and still approximate the optimal policy as best as possible. So you see that almost always when you're looking at good policies. They have some balancing between frequency and recency of access. Okay, Windows. Windows relies on processes. This is what I was saying before. Windows relies on processes to say, this is roughly my working set size. Okay. Now, when you say your working set size in Windows, you actually mean something a little bit different, which is irritating because you're saying this is my working set, but what you really mean is this is how many frames I'd like to have. And you might say, well, how is that different than your working set? Well, remember that your working set is the number of pages you're using, and the resident set is you saying this is how many frames I'd like. Your estimate of how many frames you need may not match the actual size of your working set. So let's hope programs guess well when they're guessing what their resident size should be. So anyway, this is the approach of Windows. And as I say here, if the process's actual working set is larger than the resident set, then you're going to be a faulty process. You're going to generate a lot of page faults because Windows is going to keep you roughly within your resident set size, even though that's smaller than your actual working set size. Now, there are default minimum and maximum working set sizes. And it's in air quotes on the slide because it's the resident set size, not the working set size. So processes sort of have this range of values that they are given for a default resident set size. And you can see what those defaults are on the slide. The virtual address space may be much larger. That's just the way virtual memory works. So it's not a big deal. If you have a process that knows it's going to need to work with a lot of memory, then it can tell the OS, hey, I'm a big, beefy process, and I have a large working set, and I need to ask Windows, can I have a really large resident set size so that my working set fits into all, so I can have enough frames basically to hold my working set. And so a process can do that. And of course, there's various constraints on how processes are able to do this in Windows, so that you can't just have one process sort of denial of service attack the other processes by, gobbling up all the memory. Okay, let's see. So if the page fault rate becomes high in Windows, so Windows uses the page fault rate, page fault frequency to examine paging decisions. And it has this mechanism called trimming, where it goes through all the processes and says, I want you to turn back some of your frames. I want you to turn back some of your resident set size so that we can satisfy memory requirements. And so what Windows will do is say, I need this much memory back because I'm seeing some problems. And when Windows does that, it tries to overestimate how much it needs because it can never be sure that it's actually going to satisfy its need. And if it just barely misses its need, it doesn't want to run a second time and run a third time and just sort of try to get all the memory scraped together. So it overestimates its need just in case it will come up short so that it doesn't have to do this multiple times. I hope you're starting to see how sort of heuristic-based and ad hoc operating system implementations can be. You just sort of say, I think this approach will work okay, and then you build it and see if it works okay. All right, so you have an aging mechanism for keeping track of the working set size in processes. And so the oldest pages are going to be reclaimed first to avoid faults. And the other thing about the trimming mechanism in Windows is if it reaches its required memory needs early in the trimming process, it keeps going because it doesn't want processes to be penalized just because they appear early in the sequence of processes being trimmed. So it goes through all of them so that it can be fair about taking away pages from processes, which I think is pretty funny. It tries to be equitable in how it affects all the processes when it's doing this trimming mechanism. Okay, and the last thing that I'll mention here is that both Windows and Linux use page frame pools. It's such a great idea. If I were building an OS, this is like totally what would be in the virtual memory system. It obviously increases the kind of information you have to track because if you get a fault on a page that's in the free pool, you got to be able to pull it out of the free pool. But it's really a clever mechanism to make sure that when a fault occurs, you basically never have to do eviction of the old contents because they're already clean. You basically only have to do the load and you get to take that frame away virtually instantaneously. So that's why free page frame pools are great. That's one of the reasons. The other reason is you can have a simple pager and have it make bad decisions that can be undone if they were in fact bad decisions. So there's a couple of big benefits from page frame pools. Okay, so pages are reclaimed by the virtual memory system. They go to either, remember, dirty page pool or clean page pool based on if the page contents are dirty. And the dirty page pool is slowly migrated to the clean page pool through writes to swap or the backing file. And if you have a fault against one of the pages in one of these pools, then it just gets pulled out of the pool and put back into the process. Nice, intelligent, efficient kind of solution. Okay, so that's everything that I have to say about virtual memory, unless people have questions on Piazza or in office hours or things like that. But that's all the lectures we have. What we're going to talk about next time is file systems. We're going to start talking about the high-level details of file systems. You'll notice that the CS124 coverage of file systems is pretty high level. It's kind of old too. I don't want to get ahead of myself, but I'll tell you why as we get into the discussions. Modern file systems are way more clever than the older versions, and the change from spinning magnetic disks to solid state drives has dramatically changed the needs that file systems need to satisfy. So I'll talk a little bit about that in the future, but we'll pick that up on the next class. See you next time.